This is video 3 for the mechanical waves unit. For this one, we're going to begin by talking about standing waves. These are waves that appear to be standing still. They are a pattern that results when two or more waves of the same frequency, same wavelength, same amplitude travel in opposite directions and interfere. Standing waves are the result of the addition of incident and reflected waves that are confined to a region and have nodes and antinodes. So here's what happens. We send a wave pulse or a periodic wave down a string. It hits a fixed boundary and then reflects, and it is upside down, or it's inverted when it reflects. Well, now we have a wave. We send a second wave. This is more periodic. We send another wave, and when the second wave encounters the first wave coming back, it can interfere with constructive and destructive interference. And we continue doing this, and we can set up things called standing waves. And basically, different frequencies of oscillations create different standing wave patterns. So there's a frequency that will make this look kind of like a jump rope. There's a second frequency that will have two of these, like two miniature jump ropes going. And then there's a third frequency that will have three little miniature, and so on and so forth. There can be an infinite number of different standing waves. Now, when we take a look at a standing wave, we have important things. First off, we have the nodes. This is where the destructive interference happens. And then we have antinodes. This is where the constructive interference happens. Now, when you hear a violin or a guitar or a piano playing a single note, you may think that you're only hearing one standing wave or one frequency on the string. However, there are actually several standing waves on that same string at the same time, each with its own wavelength and frequency. So the sound that you hear from most instruments consists of multiple frequencies. The possible wavelengths of a standing wave is determined by the size of the region in which it's confined. So we'll call each of these frequencies embedded in the sound a harmonic. So we have the first harmonic, the second harmonic, third, fourth, so on and so forth. And if I take a look at wavelength, so for the first one, the fundamental here, notice that the wavelength is 1/2 L. So where L is the overall length. Now for all four of these, notice that L does not change. So if I wanted to get a full wavelength, where a full wavelength is like a complete sine curve, if you will. If I wanted to get a full wavelength, I would need to take that length and multiply it by 2. For the second harmonic, notice that this wavelength equals L. For the third harmonic, that wavelength is going to equal 2/3 L. And then for the fourth one, one wavelength is 1/2. And actually, I see that I made a mistake. This first one up here, I apologize. That first harmonic, apologize. If we wanted to get a full wavelength, I need to multiply it by 2. All right, now, doing a little bit more math here, velocity equals wavelength times frequency. And v is going to be the speed of the wave, wavelength. So basically, I can go through and I can calculate the frequencies for each one of these. So I'm going to put some numbers here. 1, 2, 3, 4. So for the first, second, third, and fourth harmonic. And if I were to calculate the frequency for the first harmonic, that would equal v over lambda, which would equal v over 2L. And and I can do this for each one of these. Now these all kind of look a little different, but I can start to make these look a little bit the same. So for instance, I can put a 1 up here, so 1v over 2l, or I can do 2v over 2l, or 3v over 2l, or 4v over 2l. I can basically put these all over 2l. And what F1, F2, F3, F4, what those are frequencies. So if I were to put a little tiny machine down here that can oscillate the end of that string up and down, if that thing oscillates with the frequency of F1, it'll produce the first harmonic, or the first standing wave on that string. If I oscillate it with a frequency F2, I will see that second pattern on the string, and then so on and so forth. So to get a general formula, looking at this pattern here, I see what I need is this frequency equals something, I'll call it N times V over 2L, where N equals some integer. So this will give me a way of calculating the frequency that will produce a standing wave on that string. So notice if I found the first harmonic, let's say the first harmonic is 100 hertz. So if I make this machine vibrate at 100 hertz, it'll produce that first harmonic, or that first standing wave. If I increase the frequency to 200 hertz, I would see the second one. If I increased it to 300 hertz, I would see the third one. If I increased it to 400 hertz, I'd see the fourth pattern. So on and so forth. If I made this thing vibrate at 150 hertz, however, I would see nothing on the string, because 150 hertz is not a frequency that produces a standing wave. So we see for a string, all standing waves are integer multiples of the fundamental. Now let's talk about a column of air. We can have standing waves in a column of air as well. So if I have an instrument like an organ pipe, a trumpet, tuba, a flute, clarinet, the greatest instrument ever made, saxophone, I can take a look at standing waves inside those instruments. Now there are two basic types, and they're all pipes. They're pipes of air. I've got a pipe that is opened at both ends, and I've got a pipe that is opened at one end but closed at the other. So let's take a look at the first one, opened at both ends. So this is going to be identical to the string, except for a string we had nodes at each end. For here we're going to have antinodes at each end. So this right here represents the first harmonic, and L is the length of it. And just some things to notice with a standing wave. It might be kind of hard to see, but you guys, hopefully you can see that this is like half of a wavelength. So if I wanted to get a wavelength, I need to multiply the length of the tube by 2. For this next one, maybe if I think about it in terms of cosine instead of sine, I see that I get one complete cosine, so the wavelength equals the length of the pipe. I got one cosine and kind of a half here, or third. So this time it's that, and then here I get like 2 cosine curves, so lambda equals that. So when I go to calculate the frequencies, the fundamental, and once again notice I can put all of those over 2L, and I get 1V over 2L, 2V over 2L, 3v over 2l, 4v over 2l. So the math is actually identical. So for standing waves and a pipe open at both ends, I get the same exact mathematical model. And it's just like a string, except that for a string we had nodes at each end. For pipes we have to have antinodes at each end. A flute is an example of this, and a flute models this pretty accurately. The next type is more like an organ pipe, where it's opened at one end, closed at the other. So here we have to have an antinode at the open end and a node at the closed end. So this time, notice that this is only making 1/4 of a complete wavelength. So if I wanted a complete wavelength, I need to take the length of the pipe and multiply it by 4. The next harmonic, notice that I'm only getting 3/4 of a complete wavelength. So I'd have to have 4/3 the length of the L to get a complete wavelength. For this one, notice I have 1 1/4 wavelengths. So I would have to have 4/5 of the pipe to have a complete wavelength. And then the next one, here's 1 1/2. So I'd have to have, well, it's not really 1 1/2, it's basically I'd have to have 4/7 of that pipe to have that. So for the frequencies, I get V over 4L. The next one, I get 3V over 4L. The next one, I get 5V over 4L, 7V over 4L. So the model this time it's now over 4L instead of 2L, and this time N only equals odd integers. So the first harmonic is N equals 1, the second harmonic is N equals 3, the third harmonic is N equals 5, the fourth harmonic is N equals 7, and so on and so forth. So in this case, here we have an antinode at the opened end, a node at the closed end. Clarinets are a good example of this also, and that's because the reed is closed about 50% of the time. That kind of gives a clarinet its buzzy kind of sound. Okay, so there's a lot to take in this one, so we will stop the video here that we can kind of review it. We'll do a lot of examples in class. I do notice that there are a lot of standing wave type questions on the AP exam, so this is something we want to really reinforce. So we'll stop the video here.